Now, when actually doing computational chemistry, ab initio computational chemistry, there are kind of two parts that we have to specify about our calculation. One is the method, and the method is how we actually do the calculation. And so this roughly tells you whether are you using variational theory and what approximations are you using to do so. So this would be variational versus perturbation theory approaches. And then how to actually implement these, there are several different ways of doing this. And these all have various acronyms that describe them. There's things like MP2, this is a perturbation theory approach. Moeller-Plusset second order perturbation theory. You don't have to memorize that. Or things like Hartree-Fock, which we've talked about briefly when we talked about the helium atom. Hartree-Fock is basically not used anymore because of the lack of consideration of electron correlation, but it is sort of the basis on which a lot of these other methods are built. Right, and so there's these various acronyms. There's a coupled cluster is another one. And I don't personally understand all the details of basically any of these since I'm not a computational chemist myself. But the methods that are available, there are trade-offs between accuracy and cost in computational resources and in how long it'll take. And so there's with methods, there's always a trade-off between accuracy and cost. So generally speaking, and there are exceptions, but generally, the more accurate your method that you choose is, say if we're thinking about perturbation theory, right? This is a second order perturbation theory, but you can go to third order, you can go to fourth order even, right? You can keep adding more orders, and it increases the accuracy, but generally not by a lot in comparison to how much longer the calculations will take. And so there's this trade-off in the methods that you choose. The other major part, and we'll talk a lot more in detail about the second part of a calculation that we specify, is what's known as the basis set. And this is how you build your trial wave functions. Right, so we need ways to represent our electrons that are present in these molecules, and our basis set tells us how do we represent the orbitals that we're going to use to add and multiply together to create the trial functions that we're going to use in our variational or perturbation theory calculation. So how you build your wave functions. Right, so a lot of calculations rely on the variational principle that if we get a lower energy, that we got a better result. And so to be able to use variational theory, we have to have trial wave functions that we can use. And the basis set specifies how you build up these electron orbitals, your atomic orbitals that you're going to combine to form your molecular orbitals, just as we looked at with diatomics and polyatomic molecules, how we can create these molecular orbitals. So in the next video, we'll start talking a little bit more about basis sets.